All right. Those series of noises tell me it's 1 o'clock, so it's time to get started. Welcome everybody to this week's Green Bank Observatory Community Zoom. I'm Jim Jackson, the director of the observatory. Just a few announcements before we get started with the talk. The call for proposals for semester 2023A is now available. Proposals are due 1st of August. If you want some training on how to plan for these proposals, there are proposal planning workshops July 12th and 15th. So please check our observatory website for those details. Good news is that the ultra wideband receiver, which goes from 700 megahertz to 4 gigahertz, should be available for semester 2023A. The receiver underwent some tests on the telescope that were quite successful, and we overcame a lot of the problems that were initially identified in the first round of tests. So all is well, things are going well with that receiver, and pending successful commissioning, that receiver will be available to the community. So we will definitely post details when the commissioning phase is when we have completed the commission. Another announcement, there is a K-band workshop for current and future science with the K-band at the Green Bank Telescope. I believe Larry Morgan, yes, has just posted the link, so it's there in the chat line if you want to see the link. You can register for that meeting now. It is in October. So that should be a good meeting, and looking forward to that, your participation in that. We had a successful high velocity cloud workshop last week. Kudos to Jay Lockman. I'm sorry, I had the wrong dates for the K-band. It's the 19th to 21st of September. I was confusing my meetings. We had a successful high velocity cloud workshop. Thank you, Jay Lockman, for organizing that. I attended as much as I could. It was a terrific meeting, and I was very, very pleased to see people on campus again, interacting scientifically, some really fantastic talks. Well, it was great to connect a kind of diverse community of observers and theorists and modelers, and I thought it was a smashing success. So that's all the announcements I have, so I'll hand it off to Jay Lockman, who will now introduce today's speaker.
Thanks very much, Jim. Today's speaker is Scott Ransom from NRAO, speaking about NANOGrav and the road to nanoHertz gravitational wave detection. Let me remind everyone to submit questions when Scott's done through the Q&A buttons on the lower right of your screen, and also remind you that this session is being recorded for later viewing, and we will be available on our website. So take it away, Scott.
All right, great. Thanks, Jay. Let me get the screen sharing logistics done here. Hopefully this will work. And then start from first slide. This should take a second to show up. Let me know if you're seeing my slide.
We've got it.
Awesome, great. Well, thanks a lot. It's a pleasure to be here. So my name's Scott Ransom. I'm an astronomer at NRAO and a research professor at the University of Virginia. And I'm currently the chair of the NANGrav organization, which is what I'm going to be talking about today, because we are big users and fans of GBO and the GBT in particular for what our particular science is. And that is to hopefully very soon directly detect very long wavelength gravitational waves that are moving through all of us right now and jiggling the Earth, and they're caused by supermassive black holes that are in binaries because galaxies are merging throughout the whole universe. So it has a whole bunch of great astronomical buzzwords: supermassive black hole, galaxies, collisions, gravitational waves, millisecond pulsars. And it's all in this amazing project that's been going on for almost 15 years now. So the NANGrav collaboration is grown a lot. We have about 140 students and scientists over something like 40 different institutions. And here's at least the majority of our logos of our various institutions. We're a very welcoming organization. If you're interested in the supermassive black holes throughout the universe, the way galaxies evolve and collide, and how gravitational waves might influence those, we welcome you as members, and you can go to nanograv.org and learn about that. It's not just NANGrav that's trying to do the science. There's 3 other what are known as the pulsar timing arrays that have been established and have been working for about over the last dozen to 15 years on this. NANGrav is one of them in North America. There's also the Parkes pulsar timing array, which uses the Parkes radio telescope in Australia, and the European pulsar timing array, which uses a variety of European telescopes. And altogether, we make up what's known as the International Pulsar Timing Array. And together, we should do much better than we can individually do for a variety of reasons, but it's way more difficult to do that. So we're always a little bit behind in the IPTA compared to what each of the individual PTAs does. And I should also mention that there's several emerging PTAs that are coming online right now. There's an Indian PTA that's using the GMRT telescope in India. The Meerkat telescope, there's now in South Africa, there's a South African PTA. And all of these groups, along with the FAST telescope and a Chinese PTA, which hasn't quite yet established itself as an actual PTA, but they're all going to be becoming part of the IPTA over the next few years. And hopefully you'll be hearing a lot more about nanohertz frequency gravitational waves. So I mentioned that we think that our primary source of these gravitational waves are from supermassive black hole binaries. And these things happen just from the way that galaxies grow with time. When gas goes to the center of their galaxies, there's supermassive black holes in almost every galaxy. And then as the universe evolves with time, those galaxies merge, and the friction causes those black holes to eventually merge near the centers of the galaxies. And the cool thing is that when these supermassive black holes, and I'm talking billions of times the mass of our sun, when they start orbiting on years time scales, so these are not the very, very fast, rapidly orbiting stellar mass black holes that LIGO and Virgo are detecting. These are orbiting on years or even decades time scales. They are pumping out these incredibly long wavelength light years in wavelength gravitational waves that are pervading the whole universe. And if here in our galaxy, if we use a bunch of millisecond pulsars and very, very precisely measure when their pulses are arriving at Earth, what we can tell is that the Earth ends up jiggling back and forth, wobbling due to these gravitational waves. That changes the light path distance between us and the pulsars due to the gravitational waves, and we can measure that. That's how precise these millisecond pulsars are when we time them properly. And by timing, I simply mean we're literally measuring when each pulse from all of these dozens of pulsars arrives at our telescopes. And we can do that down to roughly 100 nanosecond precision for the brightest and best timing pulsars. So how does this fit in with the other gravitational wave projects that are out there? Well, you've probably all heard of LIGO and Virgo. That's at the right-hand side of this diagram. That's the high frequency end. So this is the gravitational wave spectrum. And so all of the amazing results that have happened from LIGO are happening at tens of hertz. So very, very rapid at the very end of these in spirals of these black hole binaries. In the next decade, LISA is going to launch, and that's going to detect thousands to millions of solar mass black hole binaries in the millihertz frequency range. And PTAs, the pulsar timing arrays, are at the left edge of this diagram. We're kind of like the radio wave portion of the gravitational wave spectrum. And the pulsar timing arrays are sensitive to billions of solar mass black hole binaries that are on years to decades timescales in their orbits. And so the neat thing is that we're probing different parts of the spectrum, and we're going to see different sources. So we're very complementary to each other. And that's one of the reasons why it's exciting that LIGO has opened up the gravitational wave universe for observations. And we're hoping to be the second observing band that's going to enable study into that spectrum. So in the past, we've been using the Arecibo and GBT for our observations, and they've been super critical for our observations. And amazingly, each of those two telescopes provided about 50% of our gravitational wave sensitivity. Arecibo was a much more sensitive telescope, so the pulsars that it could see, and that's shown in this band that's on the sky here. I don't know if you can, probably can't see my cursor, but maybe you can. If you can, it's this band right here. Those are the parts of the sky that Arecibo could see. And so if the stars and diamonds are in that band, Arecibo would do excellent. But the GBT has a much bigger sky coverage, so we can see a bunch more pulsars with the GBT than we could see with Arecibo. And that, even though it's not as sensitive, that gives us a whole bunch of gravitational wave sensitivity. Of course, as you probably know, there was a devastating loss for the astronomical community and certainly for NANGrav and pulsar science and the island of Puerto Rico when Arecibo collapsed catastrophically in December of 2020. And it's not coming back anytime soon, if ever, it really is a terrible loss for astronomy in general. And really, truly, especially, I think, I'm very biased, but for pulsars, Arecibo had an incredible legacy of amazing discoveries for pulsars and fast radio bursts. And this is just a list of some of its home runs over the years, including the Nobel Prize for Taylor and Hulse and the first binary pulsar, which showed evidence for gravitational waves. So that's been terrible. And I always get asked, since this has happened, does this kill NANGrav? And the answer is no. It's definitely a setback, but I'll talk about how we're fixing that. So in the past, this is what our observing program looked like. Split between Arecibo and Green Bank, each of those telescopes observed several dozen pulsars, just slightly more than 3 dozen pulsars in each of those telescopes, and then a handful of other pulsars with the Very Large Array. And then CHIME, the telescope that's done great FRB work in Canada, has been observing at lower frequencies, which really helps us with interstellar medium for almost all of for all the NANGrav pulsars in the north, at least, which really helps us with the interstellar medium. But with the loss of Arecibo, that was a major setback, since that's almost half of our pulsars. So what's happened over the last year and a half, is that we managed to get a lovely and amazing grant from the Gordon and Betty Moore Foundation that, combined with some funds from the NSF's Physics Frontier Center, which is our primary funding source for NANGrav, it fully funds our observing program, an expanded observing program at the GBT. And so the GBT now observes about 70 millisecond pulsars every 4 weeks. It's about 600 hours per year, to the cost of about $1 million per year. So that's an incredible grant for us, and it allows us to continue our science. And so we're still plugging along. And I also want to point out that the CHIME telescope has stepped up, because those daily observations of the northern pulsars have allowed us to stop observing with the GBT at lower frequencies, at least for some of our pulsars, which has helped us budget appropriately for the use of GBT time. So what we've done over the years, we've had multiple data releases, and this is a really busy plot. Every dot on this plot is a single observation with the telescope. And at the bottom right-hand corner, you can see our first data release in that little red square. And those rectangles keep getting bigger as we add more pulsars. Every column on this plot is a new pulsar, and time is progressing from the bottom to the top of the plot. And if you look at this whole plot right now, that basically covers what we're calling our 15-year data release, which we've now finished. And our gravitational wave working group is very, very carefully analyzing those data. What we've published so far is the next smaller rectangle, known as the 12.5 data release. And why I'm pretty excited is that in that data release, we saw tentative, very interesting hints of low frequency signals in our data. So this is a little bit technical, so I'll kind of just breeze over this. But if you look at that left-hand plot, what you can see is these two. Hopefully you can see my cursor again. This data point and this data point are much above the levels of all these other data points over here. That's a spectrum, a frequency spectrum. And those left-hand data points are the lowest frequencies that are visible in our timing of the pulsars in our data. And if we start seeing gravitational waves, we should start seeing these low frequency wiggles in our pulsar timing data, and it should look just like that. And we should see those low frequencies in multiple pulsars. And that's exactly what we're starting to see, an uncorrelated common, what we call red noise process in our data. and it was highly significant in the 12.5-year data set. So that's excellent. This is what it kind of looks like in a single pulsar. This is what pulsar timing residuals look like over the course of more than a decade. This little wiggle right here is exactly what red noise looks like. And so that's what we're starting to see in many of our pulsars. Unfortunately, the smoking gun of gravitational waves is a very specific correlated signal from the sky, spatial correlations, which cause this blue curve in these diagrams. It's known as the Hellings and Downs curve. And we're not seeing that yet. And so that's why we can't say that we're seeing gravitational waves. However, what we can tell you is that if we continue to take data, and we already have a couple more years of data in the bank, we're hoping to see this very particular signal, which shows definitively that what we're seeing is gravitational waves rather than something else. But even these initial hints made the community quite excited. There's hundreds and hundreds of citations already, even though we just published this paper a year and a half ago. We have some interesting comments about pulsar timing and gravitational wave detection. So people are becoming aware that this is a real way that we can actually probe the gravitational wave universe. And predicting in the future, this plot is a little too complicated to go into in detail right now, but this shows us that as time goes on to the right, we fully expect that if what we're seeing is gravitational waves, that within the next year or so, we should have a signal to noise ratio of a true gravitational wave detection of about 5 or so, which is pretty awesome. And it will quickly grow after that. So we're quite excited and optimistic right now. And in the meantime, all of these great millisecond pulsar timing observations are doing a whole bunch of other awesome pulsar type science, like measuring neutron star masses. And here's my former student, Thankful Cromarty, who's now an Einstein Fellow at Cornell. This amazing paper she led, which was published in 2020, and it's one of the highest cited Green Bank papers already, even though it's only 2 years old, because of the importance of these high mass neutron stars. The last thing I want to mention basically is another fantastic thing that the Gordon and Betty Moore Foundation have done for NANOGrav and for Green Bank, which is going to help hopefully some of the rest of the community. And that is that they've funded this amazing new ultra wideband receiver for the GBT. The Green Bank staff of engineers and scientists and scientific programmers have done a fantastic job over the last 2 years building this system. And it's just recently got its first light observations on the GBT. This plot on the right here shows one of our NANOGrav pulsars observed over the full observing band. And if you can see the scale on this plot, hopefully you can see my cursor once again. This goes from about 800 megahertz or 750 megahertz basically up to 4 gigahertz. And the pulsar is visible over the whole thing. That is astonishing. And so we'll be able to do great pulsar work, FRB work, and as well as some other spectral line type work with this amazing receiver, which will hopefully, as Jim mentioned at the beginning of this, be fully available for scientific use by the community starting in a couple months. And just to compare what we have had, these are the 2 receivers that NANOGrav has been using for all of our observations. We've had to use 2 separate observations for each pulsar, one at 820 megahertz, and that's the full band shown there, and one at L band, roughly 1.4 gigahertz, which is shown in that second rectangle. And we have to combine those, even though they're separated over multiple days, to help us remove the interstellar medium effects on our pulsars. But with this new ultra wideband system, in a single shot, we're going to get much, much better data, and should be about a factor of 2 better pulsar timing for each of our pulsars. So we're really quite excited about this. And huge thanks go once again to the Gordon and Betty Moore Foundation and the fantastic Green Bank staff who've helped make this possible. So to summarize, as you can tell, I'm pretty excited about this. NANOGrav is doing great, and we're really optimistic for the near future, even though the loss of Arecibo was terrible. But it's not killing us. And because of the Gordon and Betty Moore Foundation and the NSF Physics Frontier Center and the GBT and GBO, we're able to continue on, and our sensitivity is still improving with time. Our 15-year data release is finished, and our detection working group is working hard on it. And we're hoping to have a paper submitted along with papers from our other PTA colleagues. We're working in conjunction with them so that we can all publish our most recent data sets basically at the same time. By the end of this year, we're hoping to submit. So hopefully by spring of 2023, to hear really exciting things from the pulsar timing array community. And when the IPTA manages sometime over the next year or two to analyze all these data together, we should have an even more spectacular result. And in the meantime, we'll be hopefully continue to pumping out great science, such as other massive neutron stars and stuff. So thanks to GBO and the GBT and the fantastic staff there. And we're really happy with where NANOGrav's going. Thanks.
Thanks very much, Scott, for an excellent presentation. Let me remind people to submit questions through the Q&A button on the lower right, and we have one already. Has the NanoGrav limit on the density of supermassive black hole binaries produced by major mergers improved since your 2021 AppJ paper?
Well, internally, we're looking at the data and things look good. I can't really give any kind of details. So we haven't published anything because all of this, what we do is we work with data releases. So that 2021 AppJ paper came with what was known as our 12.5-year data release. And actually, I have one backup slide that'll help me answer this question. So these are kind of like LIGO noise curves that show how our sensitivity to the gravitational wave background has improved. And the orange curve was our 11-year data set. The blue curve is our 12.5-year data set. And if we add 2.5 more years of data, which we have not yet released to the public yet, but those are the data that our current gravitational wave group is working on, what you can kind of guess or project that if things stays the way they are, we're going to be shifted down and to the left again with the next data release. That's our predictions. And so the answer is yes, if things continue to look good, we should continue to improve on this plot. And remember, this is a log plot. So every small improvement here is a pretty big improvement. Once these papers get published early next year, you should see hopefully pretty darn good improvements in what we can say astrophysically about merging supermassive black holes.
Okay, there's a more technical part of that question that I'll let you answer, Scott, later offline.
Okay.
Any other questions or comments from the audience?
Hey, Scott, I'm going to ask a question. I can't go in through Q&A, but so tell me a little bit more about how ultra wideband will change your life. So I know you can get both frequencies at once, and therefore you can get the dispersion measure. How will it improve your pulsar timing accuracy, your sensitivity? I mean, what is this? Is this a factor of 2 improvement? Is this an order of magnitude improvement?
Yeah, so that's a great question, and it's a complicated answer because it involves many things together, and it also depends on the individual pulsars that we're observing. Because what happens, some pulsars are very much out of the galactic plane and are really heavily affected by diffractive scintillation, for instance. So some days they're really bright, some days they're really faint. Well, this should let us catch many scintils, so we'll get many of the bright parts of the band, and it should even out their flux density over time, which is beneficial for us in some ways. For the pulsars that are near the galactic plane, for instance, where we're looking through a lot of the interstellar medium, this ultra wideband will really help us nail down the dispersion measure and measure the scattering properties towards each of those pulsars at every observation, every time we observe. So some of these pulsars we expect will get more than a factor of 2 improvement in timing precision. Some of them, if they're not really heavily scintillating, if they don't have a ton of interstellar medium effects, we might not get quite as much as a factor of 2 improvement. But the average number that we kind of think, assuming we manage to get to the T-cis levels that we, our goals for the receiver, our sensitivity limits and goals for the receiver, I think on average over these many dozens of pulsars, it really is a factor of 2 improvement using the same amount of telescope time, which is a game changer for us.
Okay, we have another question that has 2 parts. First, does the greater sensitivity allow for you to detect more distant pulsars, perhaps extragalactic pulsars? And then the second part is, can you speak about directional identification of the gravitational signals?
Yeah, so for the first one, the big thing about pulsars to remember, especially millisecond pulsars, is they're really faint sources. So even though we're timing with the GBT about 70 millisecond pulsars, the vast majority of those are in our little neighborhood of the galaxy. They're only within, say, 3 or 4 kiloparsecs. And it's 8 kiloparsecs to the center of our galaxy. So they really are in our own little corner of the galaxy. So we're probably not going to be able to do millisecond pulsars outside of our galaxy, but having a factor of 2 better timing precision and therefore sensitivity will let us bring in more distant pulsars within our galaxy and make them timable for gravitational wave detection. And then the second part of the question, I've forgotten. Oh, right.
Direction of the gravitational wave signals.
Yeah, so what we think is going to happen as pulsar timing arrays start to detect gravitational waves in the nanohertz regime is we think we're very likely going to detect the background signal first. So it's kind of the overall hum of all of these sources merging throughout the whole universe. It's kind of like the conversations in a crowded room. But then as we continue to measure that very precisely, we'll be able to start picking out the individual conversations that of the pairs of people who are talking. So those are the individual signals. And we should be able to point roughly, and this is the problem with using nanohertz signals, because the gravitational wavelength is years. And if you look at lambda over d, the resolution of any kind of instrument studying any kind of wave phenomena, we're going to be able to say, oh, that source is kind of over here in the sky. So it's going to be a big error region, but we should be able to say over here is where it is. And then hopefully things like the Rubin telescope and the LSST survey will be able to say, hey, we see a periodic signal in that region of the sky. You've nailed it. So that's what we're really hoping for over the next decade.
Okay, so another question. Do the signals you're detecting give information about supermassive black hole spin?
They could potentially, but that's going to take some pretty high signal to noise detection. So we'll have to see individual signals, and we'll have to very, very carefully be able to trace basically the sinusoid of as that binary is going towards merger. It would help if general relativity is not the correct theory of gravity, because that does weird things to the polarizations of the gravitational waves, and the spins can really affect those polarizations. But even if everything works perfectly, this is probably going to take a decade plus from now, at least, to make any kind of really significant measurement that are related to the spins of the individual black holes.
Okay, thank you, Scott. Those are all of the questions that we've had to come in. And so let me thank you again, Scott, for a most interesting and fascinating presentation. Let me remind everybody, in 2 weeks, we will have another in this series. Jane Greaves of Cardiff University will be speaking on GBT photometry, seeking pebbles in protoplanetary disks. And let me remind everybody once again that the webinar has been recorded and then you can view it later on. We'll see you in 2 weeks.